Welcome to a new edition of Math and Physics is Fun, at least if using proper tools. In this video we want to examine damped oscillations, for which we consider a coil, cap and a resistor connected in series. Let's start Cassiopeia and open the document manager. I've prepared a document, electrical oscillations for this purpose. Let's put this here and open it. Okay, here we have a cap connected in series with a coil, and a resistor cannot be seen here, but we think of a resistor being here, the resistance of the wire. Let's look at the cap first. The cap is defined by Q over U, where Q is the charge on the cap and U the voltage to which a cap is charged. We can rearrange this like so. You C is Q over C. The next component is the coil. The voltage over the coil is given by Faraday's law. Which means if we increase the current going into this coil in this direction, the coil will react with the counter EMF voltage that is positive here and negative here to suppress a further increase of current or work against it. And the second equation we need is simply Ohm's law over the resistance of the wire. Let's put all this into one equation. You see the voltage over the cap is the voltage over the coil plus the voltage over the resistor. So we have UL plus UR. We can now simply drag all these guys into this equation. And get this one. Now we have Q and I. There's a relationship between the two, which is I is Q, the first derivative of Q. But in this case, we have a positive charge on this cap and current going into this direction, which leads to a decrease of charge on the cap. So we have to put a minus here if we define all the physical properties as described. If we do that and insert or substitute that into this equation, we get a minus here, and di over dt becomes the second derivative of q, and that's the first one. We can put this on the other side. Oh, this was wrong and now it's correct. Let's divide by L. This now is a homogeneous differential equation of the second order. Give us a number and try to solve it. Such equations are usually solved by going into it with a suitable approach. Let's try the following one. Oh. Where I is the imaginary I. Good. We need the first and the second derivative of this approach. Cassiopeia can do this for us. Another one. Okay, we can help this a bit here. I times I becomes minus, and omega times omega is omega squared. Let's rename these guys like this, so that we can easily substitute them in our equation. Okay, let's make a copy of this equation and simply drag the guys in. We can factor out this one, these two factors. Here we have it already. This one has to go, and this one. Okay, this equation is true for all t only if this equation is 0. This can easily be seen, so let's simplify it some more, get rid of this one, and end up with a simple quadratic equation that can be solved with the PQ formula. Let's change the signs. And extract P and Q. P is this term here, minus, don't forget the I, and Q is minus 1 over CL. We have a PQ formula somewhere. Let's take this one, just make a copy of it, and rename it to omega 1. So we can simply substitute into this equation now and get omega 1. Can help this a bit here. This is R over 2L. I, the minus cancels out. R over 2L minus, and we have the same here. Okay, I squared becomes minus 1. And this becomes plus. Okay, so this approach with this constant is a general solution for our differential equation. Let's substitute this into this equation. We have a sum in the power factor, so we can make a product out of this term. Let's get rid of, okay, this stays I, and here we have I times I, which gets us minus. Well, this looks better. Now we can make use of Euler. Euler said the following. E to the power of Ix let's apply this to this equation. We can rewrite it as follows. So we have one general solution, which is the sum of two functions. If this is the solution of the differential equation, then both summands must be solutions as well. So let's put this constant here, renamed, and this here. Constant factors don't make a difference, so we can get rid of this I and get this as a general solution. Oh, that's not what we had in mind. Q, T. Let's take the first derivative of this equation to get the current. Cassiopeia can do this for us. Oh, that gets nasty. Never mind. Luckily did not have to do that by hand. And we need the voltage over the cap. The voltage over the cap is, well, we can write Q is U times C. We put this on the other side, which gets us 1 over C for the voltage. Let's say at t equals 0 we have let's consider the concrete case with UO is U start and EO is 0. If we insert that into these two equations, we can determine the constants A and B for our concrete case. Let's start with the voltage. At times t equal to 0, we have U start. At t0, this gets 1. Cosinus of 0 gets 1 as well. And sine of 0 gets 0, so we can get rid of that one. Put C on the other side and get this for A. And the second limit lets us determine B. Let's make a copy of that one. We have 0 current at t0. Here we have 1. This becomes 1 again. This becomes 0. This becomes 1. This becomes 0. Okay. Did we get lost here now? Is this called 0? No, it's correct. Okay, and this one becomes 1. No, there must be a mistake. Let's start all over. I did something wrong, sorry. Let's start from scratch. This gets 0. This gets 1. This becomes 1. And this gets 0. Here we are. This becomes 1. This whole thing becomes 0. And we are left with this term. Okay, that makes more sense. Let's put this on the other side. And this as well. Which gives us the solution for A. So, the concrete solution for our problem is this voltage, this current with these two constants. Let's simply draw the function graph and drag the equation for the voltage here, for the current, which makes these two functions dependent of A and B. We don't want that. We simply drag our equations for A and B onto the function graph as well, and get the graph depending on C, the capacity, on L, R, and U start. Let's choose reasonable limits. A C of 100 microfarad, C of 100 millihenry, and R of 12 ohm, and a voltage, start voltage of 12 volt. Oh, a little less resistance maybe. Let's introduce some color. Blue for the voltage and red for the current. The current is a bit too small, so let's introduce a factor. Oh, a bit too much. Okay. Let's take 50. Much better. Okay, here we go. Let's generate logic for this document. And here we have a printable documentation of our problem. Thanks for watching.